Alrighty, well, I guess you all realize it's 12:40. So, we shall continue with fuel cells. We started talking about thermodynamics of fuel cells. We will continue to talk about thermodynamics of fuel cells, and then we'll continue with kinetics of fuel cells, and then we'll talk about platinum catalysts of fuel cells, and then we'll continue and wrap up fuel cells with the discussion of solid oxide fuel cell, although there is a solid electrolyte in there. And then that should get us to sustainability in the circular economy as the next set of, as the next part of the lecture series. So that's where we have it. And in the midst of all of that is your proposal assignment that will be due next Friday. That is a friendly reminder. So we had office hours yesterday. 3 of you came and we had a lively discussion on the questions that you had. And so I wrote down some notes of generic questions that I thought others might have. So I posted that to that set of questions to the discussion forum. So please consult the discussion forum if you think you have a generic question. It may already be answered and is there. Professor Grassman also posted a question that he received, and so and if those responses don't apply to you or are not relevant, if you have a specific material topic, then feel free to reach out to us. Any questions? Yes.
So the proposal part of this, I'm reading kind of reading it short answer here, but basically you don't address the proposal part as much until you get into the work plan of what you're actually planning to do. A lot of the rest of it is just background.
Well, the background justifies your proposed material selection or material processing. It is the background in your work plan should support your hypothesis. It depends also on what you're talking about. So, I'll reiterate what I put on the discussion forum, although I was a little bit succinct on the forum, which is you need to provide enough information so that the reader can follow along. And the reader, 2 out of 3 of the readers will be your peers. So your peers, it's fair game to assume that if the topic has been covered in class, that your peers understand that topic. So if you use terminology that we've already discussed in class, you should assume that your peers should know that as well, whether or not they were in class or not, or whatever. You should assume that that is fair game. If you use technical terms and you want to be more specific because you're normalizing by something, or you want to provide more clarity, then you should do so, and that should be provided in your background as well as your work plan. But the level of detail depends on your argument or your hypothesis. Okay, and of course, if you have questions along the way, just reach out. We are here. Okay. All righty. Continuation, thermodynamics. Let's get back to Gibbs free energy. I was saying that everything happens at the interface. Everything still happens at the interface. At least the reactions that are of interest and importance to the electrochemical performance of your fuel cell happens all at the interface. So this is where people focus their materials engineering and the processing of materials, is to get this interface as optimal as possible, because that's also where degradation will happen. So, right. So I wanted to break up, very long discussion of thermodynamics with something that's a little bit more realistic. So if you have if you're engineering a fuel cell, this goes back to the base question about, what are we talking about? We've gotten into the nitty gritty of discussing the fundamentals, the processes, but at the end of the day, you end up with a tank of gas. What can it do for you? So these are the sort of type of questions we can answer in terms of understanding, how big things are. So typically, let's say you have a fuel cell. Here's an example where if you have a fuel cell where it can produce, this number 5 standard cubic centimeter per minute, or as is commonly known, SCCM of hydrogen at 25 C and 118 in 1 atmosphere. So we're at standard temperature and pressure. So what you need to be comfortable with is converting moles of gas to mass and the volume as well. So we're talking about compressed gas. So we're talking about pressure. We're talking about volume that you can compress it in. We're talking about how much mass you can store in that specific volume. So what we want to be comfortable with is manipulating the ideal gas law. So we're assuming ideal gas state right now. There aren't gas interactions, things like that, collisions. So, we're going to go with the ideal gas law right now. So what we want to know is how much current can this fuel cell produce, right? What's the rated amperage? So we can manipulate that if we know, well, we want to know what the current is, right? And that, by definition, is the change in the charge over change in time. So that's dq dt. That's also related to NF, N being the number of electrons that you're moving, so that'd be 2, Faraday's constant, and then dN dt. But we know what dN dt is through the ideal gas law. N is the number of moles of gas that's in your system. And we know how to relate what we've been given, which is, 5 standard cubic centimeters per minute. So this rate where we have a volume per time at temperature and standard pressure. So here we can calculate what N is, but this N is also this N. So when you see the ideal gas law, you probably have seen it in the second form where it's PV equals small n RT. That's not to be confused with this small n, which is the number of electrons. So you can see here, the chemistry folks use slightly different terminology than the electrochemistry folks. But I presented in this way, hopefully to shed some clarity as to what all these variables are and how you can relate them in different equations. But normally you don't see, this if you're reading a chemistry textbook. You see more like small n. Okay. So it adds a little bit of confusion, but there are, only so number of letters in the English and Greek alphabet. Okay. All right. So n, small n over here is the number of electrons. Big N is the moles of gas. So basically, you do some algebraic maneuvering. You bring your n over because you know from ideal gas law that it's PV divided by RT. R being gas constant, temperature, you're at 25 C. Convert that to Kelvin. And so that's what you do. So you're transporting 2 electrons. Faraday's constant is here. You're at standard temperature and pressure that we know. This is the gas constant, temperature converted to Kelvin, and you get charge per time, so coulombs per second, which is converted to amperage. 1 coulomb per second is 1 amp. Okay. So that's it. It goes back to the heart of the term itself, electrochemistry. How much current you can get out is based on the chemistry that you put in. So we relate ideal gas law to that of the current that can be produced by your cell. So how many moles of gas fuel you have put in, now you can calculate how much current you can get out of your fuel cell. Okay. So the flip side is, okay, you have an engineering problem and you want to know how much gas you need for that specific application. right? If you have an appliance, you need some, input current, or you need to draw a certain current out, or you need to draw, some power out. Then you have to backtrack and say, okay, well, how much fuel do I need to input into my fuel cell to achieve that? So an example would be, if you need to operate your fuel cell for some appliance or device at 2 amps for 1 hour, so amp hour, and then you follow that up with, some different load. So there can be variable load, 5 amps at 2 hours, but some load X amps at Y hours. Okay. So you use the same relationship, but now you've inverted it because now you integrate current over time. That's charge. Surprise, that looks exactly like a battery. That's exactly what you do. Constant current over time integrated is the charge that you get out of your battery. So two sides of the same coin, same equation. So we know current over some time, your 2 amp for 1 hour load is here. And then you'll apply a 5 amp load for 2 hours. So the total charge converted to seconds, of course, the proper units, you get 43,200 coulombs, right? But the gist is you need to know, the total charge that you'll need. But we know from before that charge is related to the number of moles of gas that you have, and also the number of electrons that are being transported. So we can do algebraic manipulation, and we know the total charge divided by the number of electrons times Faraday's constant gives you this particular number. So we're just basically rearranging the equations that you've seen. So now I need 0.224 moles of hydrogen. But the question asks how much mass, right? What's the amount that somebody filling a gas tank needs to fill it to give it to you? So you just convert that using the molar mass. So 0.224 moles of hydrogen is this amount of hydrogen in grams. Pretty standard. Relating current back to now the chemistry. Okay. So these two examples, we've just manipulated I equals dq dt. That's it. That's like the reigning equation that you need to know, which applies for your batteries and your fuel cells as well. All right. So we've talked about current, which is useful, but now we also want to talk about current density, which is even more useful because it's not just the current that you can apply to, that you can get out of the fuel cell or apply. It's how much can you put through your system, your electrode, and then your cell, of course, because your cell is made up of the components. So there you want to divide the current that you're interested in, divide by the area. So let's say divide by the area of your electrode or the area of the electrolyte. But you're interested in amps per centimeter squared. So this is how we're going to normalize and compare cell to cell. So the electrochemical reaction rate, then we want to know, all right, well, if I pump in this hydrogen gas, what is the rate of conversion and oxidation so that the protons, let's say for polymer electrolyte membrane fuel cells, the polymers can then, the protons can then migrate through the polymer membrane and then react with the oxygen once the oxygen has been reduced and then produce water, right? So you're interested in the electrochemical reaction rate, and there that's capital J because we couldn't pick another letter. So that's capital J as opposed to small j, which is your current density. Okay, so not to be confused. So when you're reading literature in fuel cells, small j is the current density. So the overall electrochemical reaction rate normalized by the area, it's just the same equation manipulated. That's the number of moles over time that's reacted. So that dN dt is just then I over NF. But N is just the small n is the number of electrons in the chemical reaction. Okay, that's the number of electrons that's being transported. So the units there are moles per time per area. Okay, so dN over A dt. Okay. So the objective of fuel cells is to increase this electrochemical reaction rate. You want to be able to process and have high turnover while, so that increases your efficiency while maintaining mechanical and chemical stability of your electrode, right? You want to be able to feed in hydrogen and have the hydrogen oxidation reaction, which is this, producing protons pretty rapidly, right? You want hydrogen to come in, absorb onto your catalyst, get split, protons desorb and move. Like you want this reaction just to happen pretty fast. And it does actually happen pretty fast because it's pretty easy in the sense that relative to the other electrode where you have pumping in air, you have 21% of oxygen, then you have other gases that you have to purify out. So, you know, on this side, hydrogen oxidation is pretty standard. It's pretty straightforward. Okay, so the nitty gritty is if you have the hydrogen coming in and absorbing onto your catalyst, now you're at the interface, the metal hydride, the metal and adsorbed hydrogen will form. And what you need to do is overcome this barrier to then release the proton, and then it will migrate to the other side. So that's the energy barrier that, that you want to overcome for your reaction. So the first curve here, curve 1, where you start off with the free energy of the metal, and it sees some chemisorbed hydrogen. So, and then curve 2 is where now you've split it, the hydrogen oxidation reaction has happened, but the proton is still near the electrode. It hasn't migrated yet. So that's the energy barrier that you need to overcome on this side, on this particular interface. So the reaction rate is just standard statistical mechanics. I mean, this probability equation applies for honestly anything like heterogeneous catalysis, electrocatalysis here, but basically it, you know, what is the statistical frequency of which these gaseous species will come onto the interface. If you're in heterogeneous catalysis, it is the surface, but come to this interface, get split on the interface. So there are chemical reactions that are happening on the interface. You know, let's say it's platinum, and then that gets split. So that probability is the probability of activation, and that has, you know, some energy barrier, delta G. Okay. So then the fuel cell reaction gets split into, well, if it can be split, it'll go forward. So the hydrogen gets split in protons. That's a forward reaction in this particular case for hydrogen oxidation. But the reverse can also happen. If the protons see each other enough, they collide, the reverse reaction will happen. So obviously you want to split the hydrogen, form protons, have them migrate. You want to minimize the reverse reaction, right? You've just studied in hydrogen. Now the protons are going to collide and then form hydrogen back, which is, you know, not as useful if you're trying to run a fuel cell. So we have to split it into the forward reaction, which is J1, that's the electrochemical reaction rate, big J1. There's also a reverse reaction, and because this is the real world, statistical mechanics would say that will happen at some other rate, and that rate is this big J2. So you have competing, with every reaction in life, you have competing reaction rates, right? The forward and the backwards can happen. So your current density, if you assume, all right, well, I can design a catalyst where the forward reaction will happen. Like the conditions will be more favorable for the forward reaction to happen, for the hydrogen to split into protons, then you can safely assume that your current density, J1, is going to be related to your reaction rate times NF. And being the number of electrons in your reaction, and F is just Faraday's constant, and then J1 I've just replaced with the equation where now your e to the negative delta G 1 over RT is also related to the reactant surface concentration. So how much, of the adsorbates, of the adsorbing gas you have, and also decay rate to products. So when you form your product, so your protons being split in, your hydrogen being split into protons and electrons, right? As more protons are being produced, there's a decay rate of the amount of reactants you have. So these are competing factors, right? It's not like in this particular scenario, you're not pumping in gas like continuously. You start out with some amount of gas, you pump it in, you let it react, your reactants will decrease as you have more products, right? So that you take that into account. So you add all of this together and you get some overall like reaction rate, some J naught that says, okay, this is how the rate, the current density based on the electrochemical reaction rate of the forward and backwards.
Seeing this reaction makes me think of something. Do fuel cells need like a storage take place to deposit like the byproducts of the reaction if they don't use, or do they pretty much just use 100% of the reaction products?
So they use 100%. Now, what the products are will be varied depending on the fuel cell chemistry, right? So if you have an optimal fuel cell chemistry, as in you've chosen the best platinum, the best catalyst, let's say you put platinum down, and you have Nafion as your membrane, there will be a reaction. Your reactants will be consumed. If you put in X moles of hydrogen, that will be consumed, but how effective and efficient the number of how efficient it is splitting hydrogen into protons, and then those protons reacting with oxygen on the other side to then produce water, that isn't always 100%. But what is 100% is the consumption of hydrogen and the consumption of oxygen that you put in. Now, okay, if it's not 100% efficient, what are the other side reactions? Well, it could be a number of things. You could have two hydrogen reacting with oxygen and form peroxide. You can form H2O2. So there, your product utilization is the utilization is 100%, but the product formation is not 100% because what you wanted was H2O liquid. What you got was H2O liquid plus some like H2O2, what have you. Yeah. So there's the nuanced answer to your question. Okay. All right. So then you have current density, right? So at equilibrium, forward reaction equals backward reaction. That's your J naught. So if you read fuel cell literature and you see J naught, that's what it refers to. And then we come to the other very important equation in fuel cells and electrochemistry in general. You'll see this in corrosion as well. Understanding, reaction rates is the Butler-Volmer reaction. So here the energetics are similar in the sense that you still have your reaction, you have some chemical potential, some chemical free energy here. Your reaction, you need to overcome that. So here we're still talking about hydrogen being converted to protons, right? But now we introduce a concept called activation, the activation barrier to this electrochemical reaction. So all is not 100% PG, right? There's some over potential, there's realistically in the real world, you're going to have some concentration loss. You're going to have conditions that are away from thermodynamic equilibrium. So that is what we call voltage loss. You need to sort of overcome this barrier. So the current that can be produced by your electrochemical reaction will increase with what's called the activation over voltage, right? So here is the electrical energy. So what's lost, there's this term called eta. So this is the ideal state of your electrical energy, from here is the electrode interface. As you move farther away, your electrical energy increases, but realistically what you get is this dashed line. It's scaled by this eta, this activation over voltage or over potential. Okay. And that could be due to, honestly, a number of things. It could just be due to, materials design. It could be, just inefficiencies in your catalyst. But now what we do is we take the same current density and we scale it by this. We scale it by this alpha and this eta. So the alpha tells you, oh, here you go. So the alpha tells you it's the transfer coefficient. And so it's the symmetry of the activation energy. What that means is what I showed you before was you have a chemical reaction, you start off here, you overcome it, and you get, to some product state. Alpha tells you how asymmetric it really is. And we won't be crunching some numbers, but I wanted to show you the explicit form of the current density, because what you get is you can calculate the current density measured at, the initial reactant concentration and the product concentration, but the inefficiencies that I just talked about will scale the real current density that you measure by all of this. Right. So that is the Butler-Volmer equation. It tells you the transfer coefficient. It takes into account the transfer coefficient and how much of the activation over potential will impact the current density that you measure. So you'll see some version of this in corrosion as well. Okay, so the other form is that of assessing fuel cells is looking at the Tafel equation. So let's say this is what happens when an overpotential is really large. And by large, that's 50 millivolts to 100 millivolts at room temperature. You've scaled the J naught by this exponential. So the measured current density is this J. And so if you take log of both sides, you can calculate what eta is, what this overpotential is. And then you can say, okay, well, if I just say this is A and this is Y intercept, and this is the X, the variable ln of J, you get the Tafel equation. So basically you just lump everything into a linear line, okay, a linear regression. And so that's what you get. So here you can see, although I cut off the x-axis a little bit, sorry about that. Well, yeah, no, that I think it's still legible, but basically you can calculate this eta and you can extrapolate and fit, what this is for voltage versus the current density, and you get out, you can fit the Tafel equation to get out these parameters of what alpha and V are. All right, so that was a very deep dive into like the very nitty gritty reaction rates, but that's explicit derivation of like these equations that people use all the time. So when you read like fuel cell literature and you say, well, we fit the Tafel equation and the slope is this, so it's better. Well, what does that mean? What is the slope? So one of the values that is stated here, how do you calculate J naught? Well, J naught, if we assume that the Ford reaction happens, then the number of electrons that are transported, Faraday's constant, the reactants, the concentration of the reactants that you inputted, and then the activation barrier to overcome that, right? So then you say, okay, well, if I want to increase current density, what do I increase? You can increase the amount of reactants, right? You can just have more gas. That's fine. But the offset is if you're pumping in a lot of gas, at some point, the gas is not moving fast enough through your material. Let's say maybe your material isn't porous enough. There's going to be diffusion limitations, in which case mass transport will be limited. So it doesn't matter if you're just like pumping in a lot of fuel, your electrode can only do so much work. right? So there is some limitation to just increase the concentration, of your reactant, say, or the rate of which you're introducing your reactants. You can decrease activation barrier. That's where your catalyst comes in. You bring that down. So that's the role of the catalyst. You bring down delta G. You can also increase the current density by just increasing the temperature, right? So that's T. So if you divide a very large number, like a very large temperature, this is E to the negative of that. So you divide by a large number, so your decay is less, so your current density increases. And then you could also just increase the number of possible reaction sites. That's not listed in this equation. So it doesn't have a variable for that reason, it's just blank. And that's where catalyst material engineering comes in. So the other part, we've been talking a lot about hydrogen oxidation. The other electrode you'll need to do oxygen reduction reactions. So when you read in fuel cell literature, ORR is a huge dominant area of research for polymer electrolyte membrane fuel cells, because this reaction is difficult. Okay. It's also a huge area of research because it's hard to change or replace platinum because it's the ideal catalyst, but it's expensive, right? So what's governing, what materials you pick is the Sabatier principle. So this principle basically just tells you whatever catalyst you pick, your adsorbates need to not bind too strongly onto the electrode, a catalyst, but it can't bind too weakly either. So it's, a very fancy way of saying you need the Goldilocks of catalyst adsorption energy, or the adsorbate energy needs to be somewhere in the middle, because you want your fuel or your gas to come in, adsorb onto the surface with some reasonable binding energy, but it can't be too strong because then it'll just stay there and then your reaction won't go for it. But it can't be too weak because then it won't adsorb altogether and then your catalyst won't be actually mediating the reaction. So somewhere in between is the Goldilocks adsorption energy for the reaction to occur. So that's the Sabatier principle. This also applies to heterogeneous catalysis, where your adsorbate is in the gas phase and your catalyst is in the solid phase. So, so what do you do? Well, we talk a lot about catalytic rate and frequency turnover. These are pretty important terms for understanding, the performance of a catalyst, right? So the catalytic activity, when I say you want to increase the performance of your fuel cell, you need to increase the catalytic activity of your electrode, right? So that's the rate at which the chemical reactions occur on the surface of the catalyst. In this particular case, it's the interface of the electrode electrolyte. And the turnover frequency is the reaction per second per individual catalytic site. So how do you increase the catalytic site? Like, how do you increase the number of sites that you have in your catalyst? Yes, you read the next slide, or you just thought about the problem, or both. Or you read a paper about it. Yes. So this is the Sabatier principle. This is what's called the volcano plot. But yes, Olivia is getting to this. So platinum is high up there. So you can see here the activity is highest for platinum, and the oxygen binding energy is on the x-axis. So in catalysis, this is what people strive for. Is there some quantitative metric where I can pinpoint and basically make a volcano plot and say, well, there it is. There's the happy middle. Highest activity is in the middle for binding energy, or whatever this x-axis may be, right? So that's sort of like the goal of catalysis, is to find what is that metric that I should think about that will produce this volcano plot for me. Okay. So yes. So yes, we nanostructure platinum because of all these reasons. In the book, it's pretty fabulous in terms of having high mechanical strength, electrical conductivity, low corrosion. It's a noble metal. It's not that reactive. It can have high porosity. You manufacture it just right. Ease of manufacturing. Notice I didn't say ease of mining. And then also high catalytic activity. The mass loading of, say, a typical electrode is about 0.4 to 0.5 milligrams of platinum. So that's actually not that much per centimeter squared. But the price of platinum is $1,000 per ounce. The last time I Googled before I, finished the slide deck. So it's about $1,000. It fluctuates somewhere between like $1,000 and $1,300. Convert that to grams, that's $33 per gram, and your fuel cell requires about 0.4 right now, and DOE is trying to get it down. Department of Energy is trying to get it down to 0.1 milligrams of platinum per centimeter squared. So if you reduce the amount of platinum that you use, but you want to make it more active, you need to increase the number of surface sites, which means what Olivia just said. Okay. You can also reduce the cost of platinum by developing alloys, right? So you just take a little bit of platinum out, put in a base metal like nickel, see how much of a performance price you pay. Or you can just say, well, forget about platinum. Let's just go metal-free altogether and make some sort of carbon-based catalyst. This is a huge area of active research. But of course, the main limitation right now with metal-free catalysts is that they just don't generate as much voltage. They just don't perform as well. But that's not to say that they're not viable for very specific applications where you don't need that much. Right. So if you plot the surface area to volume ratio. So if you take a spherical model and you say, okay, I make a nanoparticle and it has this range of diameter sizes. If I calculate the surface area, divide that by the volume of that size of that particular radius, so d/2, that's the ratio I can calculate. If you plot that, you get this curve right here. And you could see if you make really small nanoparticles, aka 2 to 5 nanometers, you could see the surface area to volume ratio is very high. That means it's very active. So you can reduce the amount of platinum that you have by just nanostructuring it. You use less material, but you drive the reaction rate way up. And that's already what's being implemented in your gas vehicles, gasoline-based vehicles, where you have catalytic converters, right, to meet emission standards. This is less of an issue these days, but if you have a really, really old car, maybe we're talking about like 20 years old, this is a huge concern because your catalyst is probably dying, and by that, I mean being deactivated. But if you have a newer car, platinum, palladium nanoparticles are already loaded on cerium dioxide, and that is what is converting carbon monoxide, oxidizing into CO2 so that your car can meet emission standards. So you're not just pumping like carbon monoxide into the air. Okay. So, this is also the reason why some vehicles, if there's a theft, the catalytic converter is the first to go because it has the noble metal. Okay. And recycling too. If you want to recycle a car, you can recycle the aluminum body, or you can recycle, try to get out the platinum because that's also of value. So these are all the reactions that could potentially happen on this particular platinum surface. This is the platinum 111 surface. Platinum is face-centered cubic. So this is, if you cut through the 111 plane, you get all these atoms that look like this. And these are all the possible reactions that occur. So oxygen can come in and has several ways of splitting. It can adsorb as O2. So with the double bond itself, then becomes a single bond on platinum, or it can split and then adsorb as just an oxygen. That could happen. And then, the cascade of reactions follow. Okay. And that cascade looks something like this. And this is what people spend their lives studying, because it absolutely affects how you design your nanostructure, as in what shape your nanostructure should have, your wolf construction of your nanostructure, as well as the type of alloys that you can design in terms of nanostructuring the alloy. So on a platinum 111 surface, what you see here is the O2 can come in, it can dissociate into two oxygens. So that's the adsorbate is denoted with an asterisk. So that means, platinum, there's an oxygen. So that oxygen is now has an asterisk on it. And then it can react with also adsorb H2O, and that forms water. It can react, so it can also adsorb as platinum, something like this. So this whole species is adsorbed. And then that reacts with, let's say, a hydrogen that's on the surface. It can form this OOH that's adsorbed. And then it can take one of two processes. It can then dissociate more. And then this hydroxide or hydroxy will then react with another proton that's adsorbed, and that forms your final product of water. Or it could take this very long process and then eventually form water. What you want is the most efficient step, obviously, right? What also happens is if you can design a material that selects one but not the other step, then you don't have these reaction rates that are convoluted together. And then you also have these species that are, colliding and reacting and making your fuel cell catalyst, inefficient, basically. So that's what you want. And so you can map all this out with density functional theory. As a computational material scientist, chemist, physicist, you can actually map out all the energetics, and you map out the reaction rates that you see here. But at the end, you start off with something that's high in energy, and you end up with, let's say, H2O that's lower. And the crossing that I was talking about, it could start off as this, and then it continues, or it could then cross over and then go this way. So what you want is to be able to isolate, one reaction, so you understand what people often refer to as the structure property relations in a material, right? If I know the structure, if I design it this way, this is going to be the electrochemical property that I get out. This is the performance that I'll get at. And that is the holy grail. I said there was no holy grail, but that is a major objective in catalysis design. I wanted to note on here, some of the reactions that you may come across, these terminologies that you may come across in the literature. So depending on how the adsorbates react, so whether both, let's say, the species co-adsorb and then react, that is this Langmuir-Hinshelwood or LH type of reaction. Or you can have the Ely-Riedel, never really know how to pronounce the second one. There's several pronunciations. You can have an adsorbate come down, and then the second adsorbate reacts, and then that molecule disabsorb. All these reaction rates are heavily studied because it matters in the end how you design. So we've been talking about platinum 111 surface because that's the lowest energy surface. When you in nanostructured material, most likely it will have a lot of 111 facets exposed like this because it's the lowest energy surface in a face-centered cubic type material. But what you can do is you can make other morphologies that you see here. So you can make core shell. So you say, okay, well, if platinum is the is the most active catalyst, then why wouldn't I just make a core of my material made of something cheaper, like say nickel, and then I just coat a very thin layer of platinum on the outside, solution or spray coating or, chemical vapor deposition, whatever fancy method you want to do. The answer is yes, but then there's leaching because thermodynamics will then come into play, because then what you have is you're then created a gradient where let's say you have nickel on the inside and platinum on the outside. At the interface of platinum and nickel, or iron and platinum, or what have you, like some cheaper metal, you're going to have an interface where you sort of have an alloy. And then the alloy says, well, energetically, I prefer to be this alloy. So then you have movements. These are mobile atoms, so you'll have processes called, like Oswald ripening. You have different types of sizes of structures. You also can have something that looks like this, where the Kirkendall effect, like 1950s, material science here. These, the diffusion rates of these atoms make them mobile. So if you have something like platinum and nickel, you could start off with something that looks like this. Here's the 111 surface. Here's the 100 surface. You can have something like this, and then if you wait over time, you have the diffusion rates of these two species form these cages, and in the end, you have structures that look like this. And I think if you wait like 2 weeks, you go from the polyhedra to this empty cage. Now, why would you want an empty cage? You have more active sites. This goes back to what Olivia said. Now, not only do you have adsorbates that can adsorb onto the surface, but you can also have gas species, go into the cage, adsorb from the inside as well as the outside. So you can increase your electrochemical reaction rate. Right? So understanding how we increase electrochemical performance will dictate how we design our materials. Yes. 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 So, yes, the diffusion rate. Yes. So they are synthesizing. So the question is, are they synthesizing solution? The answer is yes. They are synthesizing solution. What this doesn't show, and now we get to the processing segue. What this doesn't show is, because this is done in solution, in order to keep all the nanoparticles from agglomerating, because the smaller nanoparticles, what will happen is they have very high surface energy, right? Let's say this is a 2 nanometer, 5 nanometer poly, in size, like diameter. Okay, it's not a sphere, but let's say it's a spherical equivalent of that. It has very high surface energy. So in order to decrease that surface energy, what it wants to do is come together with another nanoparticle, and then they form and coalesce. And then now you have a larger particle where you have decreased surface area, surface energy, and it keeps on doing that. So that's also ripening, right? In order to keep all these nanostructures apart and prevent agglomeration, there are these hydrocarbon ligands that you don't see in the schematic. So it's like C18, chains. And so the next particle will have these, and that will prevent them from agglomerating. But obviously that will prevent the catalyst from performing, because now the surfaces are not exposed. So what you do is you can deposit sonicate, throw it in some carbon powder and just sonicate the heck out of it. And then once that's deposited, you can put that in the oven. You can acid etch it. You can dunk it in a little bit of acid, and all these hydrocarbon chains go away. But now you won't have agglomeration because the particles are deposited on a support that will keep them all apart. And that's what you see in fuel cell electrode, is whatever nanostructure material you have, they're deposited on a support that keeps the particles from agglomerating. Yeah. But yes, the change in stoichiometry is dependent on the reaction, the Kirkendall effect, the fact that nickel has a different diffusivity than that of platinum. Okay, so I've gone on and harped about, platinum and nanostructure design, but, there's a lot of research also done on the support itself, to increase electrical conductivity, you want, something, a support material that can be lightweight, so you're not adding more weight to your electrode, but is highly electrically conductive, and so that's where carbon comes in. So there is a plethora of carbon that you can buy. You can buy carbon black with different, sizes. If you want to make a percolated network, and your platinum size is a certain size, you want to size match and things like that. You can, open up Vulcan's catalog, and you can just order whatever carbon you want. There's also specialized carbon structures like nanotubes if you want directionality and in electrical conduction. You can have carbon nanofibers, you can have graphene. I mean, the flavor of carbon is really up for grabs, and it's your choice. But the cheapest is just carbon black, So, as long as there's enough carbon, you will have a percolated network, and there will be electrical conductivity. It also spreads out the platinum so that they don't agglomerate. But this is also a huge area of research. Okay, so the reaction pathway, I said you want the most efficient pathway and not the other inefficient pathway. So the most efficient pathway is what's called this 4-electron pathway. So oxygen comes in, it becomes adsorbed. So this is from a 1976, I was about to say 1978, 1976 paper. People have been studying this for a long time. NASA has been studying this for a very, very long time. You can have oxygen come in, it adsorbs, and all these kinetics, all these reaction rates, K2, K3, whatever. But at the end of the day, what you want is for oxygen, adsorbed oxygen, to go through a 4-electron process and just form water. The intermediate reactions are typically what will occur as well, which is you form this peroxide that can be adsorbed, and then peroxide can also deadsorb. And now you have peroxide in your system. And peroxide can be corrosive. So then it starts etching your platinum, and then you have loss of catalyst, and you then have decreased efficiency in your fuel cell, right? But peroxide could also eventually go to water. But the short of it is you want to prevent the 2-electron reaction to happen. It's not as efficient. And once again, so you could say, okay, well, what about alloy, right? You make the same volcano plot that you see here. You see the current density and you see the binding energy. And what you get out is, well, if I want high current densities, I should just alloy with nickel. So not a surprise, 2014 science paper comes out where 3 molar equivalents of platinum to 1 molar equivalent of nickel, exposing specifically the 111 facets in your nanostructure, will get you the highest performance while decreasing the price by a little bit, because now you replace some of the platinum with nickel, right? 25%. So that's what you do. Okay, so I just have here some charts as to what kind of carbon do you want? What kind of platinum do you want? What kind of activities will you get out? So for oxygen reduction reaction, here are some of the platinum alloys. Also platinum metal doped with, let's say, species that are not metal. So we talked about alloying with 3D transition metals. You can also just alloy and dope with carbon or what have you, and nanostructuring. And you can really increase the activity. You can see here, by 2 times, 6 times, 11 times in terms of reaction rates. So, material selection and design can really increase the efficiency and decrease the cost of your catalysts. So I think this is a good place to adjourn, and we'll pick up here next time. We will be starting lecture 26, but we only have a little bit of discussion left on polymer electrolyte membrane fuel cells before we go to. Yeah, thank you. Before we go on to solid oxide fuel cells.
So of course, there's always the old problem though.
Yeah.
Platinum is ridiculously expensive.
Yes.